Hi, I'm Dave Eicher, editor of Astronomy magazine. Welcome to the last, I can't believe it, this is the last Cosmos Rewind Google Hangout, sponsored by Celestron, the great telescope company. In this Hangout today, we have a distinguished panel that will discuss the 13th and final episode of Cosmos, a SpaceTime Odyssey. Boy, it just flew past. Unafraid of the Dark was the name of this episode. We have a great panel, as always, lined up to discuss the show this week, including a special guest from space.com. So let me introduce them to you. Corey Powell, you know, the editor-at-large of Discover. Thanks, Corey, for being with us once again.
Hey, let's do it again afterward.
Well, we can do a 14th. We can keep this going here. Liz Cruzy, Associate Editor of Astronomy. Liz, great to have you back today.
Glad to be here to talk about some awesome astronomy.
Miriam Kramer, staff writer from space.com. Miriam, thank you very much for joining us today. It's a pleasure to have you.
Hey, yeah, thanks for having me. I'm excited about it.
Rich Talcott, Senior Editor of Astronomy. Rich, great to have you back.
Thanks, I wouldn't miss it.
And myself. And before we get going, we're going to go to Liz Cruzy, who is going to do the episode summary to describe for us in detail what was all of this that they called Unafraid of the Dark.
Yes, so I am going to quickly summarize the episode, which showed up on Sunday and Monday. It touched on some of the most exciting science of the current time, like dark matter and dark energy, also very mysterious science. The episode began in Alexandria 2 millennia ago, at a place that spent a very large fraction of its gross national product on acquiring knowledge, which seems like a very lovely idea. Then it was experiment time. Neil deGrasse Tyson had us pick a star and imagine it hosted dozens of planets and moons. On one of those worlds was an advanced civilization that saw itself as the center of the universe. This is the same idea that early observers thought of our own planet, imagining that everything, the sun, the planets that you saw in the sky, circled Earth. Neil then introduced us to Victor Hesse, a physicist who discovered cosmic rays, radiation coming from outer space, about a century ago. And then we fast-forwarded 2 decades to meet Fritz Zwicky, the most brilliant man you've never heard of, unless, of course, you watched the most recent Cosmos. He theorized that when a massive star dies, it collapses into a tiny and extremely dense star made of neutrons. These objects do exist, called neutron stars, and astronomers study them today. Another one of his hypotheses involved the way that galaxies within a galaxy cluster moved. Zwicky said that something invisible must be holding onto those galaxies because they move so fast that they should have been flung out. Instead, people just thought he was crazy. Then came Vera Rubin, who in the 1960s and 1970s measured how fast stars in the outer parts of dozens of galaxies were moving. Sure enough, they also were traveling too fast, unless some sort of invisible matter was holding on to them. That invisible matter weighed at least 6 times the amount that the stars and gas that's visible within a galaxy would be. Astronomers call this invisible material dark matter because they can't see it, and it's some sort of matter. There's something even crazier in our universe, and that's called dark energy. Observations in the 1990s showed us that the universe's expansion is actually speeding up, and this came as a tremendous surprise to the scientific community at large. The universe, astronomers now believe, contains less than 5% gas, planets, stars, black holes, moons, comets, all the stuff you can see. About 25% of the universe is dark matter, and that leaves about 70% as dark energy. These are all plus or minus a few percentages. So after your mind was blown by that stuff, Neil switched to the twin Voyager spacecraft that launched in the 70s and were the first probes to tour the outer planets of our solar system. He described the record that they hold, which will last about 1 billion years, so hopefully it reaches another civilization in that amount of time, and they can learn things about Earth, like how we say hello in, I think it was 59 different languages. Then Neil gave a very moving tribute to Carl Sagan and closed out the series atop the same cliffs in which it opened. The description from Sagan of the pale blue dot image that Voyager took gave me goosebumps, and I know it did the same with a number on this panel. I really do wish that more scientists could describe their work and the overall goal of science and astronomy in a similar way to move that amount of people. And finally, you, the viewer, was left at the helm of the ship of the imagination, free to use science to find out about the universe in your coming escapades, whatever they may be.
Well, thank you, Liz, very much. And I think, let's just talk a little bit about how this episode struck us. Not only did it cover dark matter and dark energy, but I think overall it was just a whole lot more astronomical than some of the series coverage of recent vintage. So I thought it was a really good episode, and sort of ended appropriately with sort of a review of Carl and of science overall and the goals and means and views of science and scientists. What did y'all think of the episode overall?
Well, I had a very similar impression. I thought it's a beautiful episode, and I thought it bookended things nicely. The very first episode of the New Cosmos started with some reflections on Carl Sagan and on Carl Sagan's relationship with Neil deGrasse Tyson and with the second generation of the show, and it closed that way as well, bringing back Carl Sagan's voice and his words and his perspective, and a whole discussion not just of the pale blue dot image, but of the Voyager spacecraft and the Voyager Golden Record, an artifact that's carrying the sounds of Earth out into space and ultimately into interstellar space. These are big, beautiful, inspiring themes. I thought it made for a very powerful ending to a show that I think this time around, even more than the first time around, is really trying to focus a lot on the concerns of the here and now, of sort of how science plays out right here on Earth. And this episode really carried it back, I think, to the more elevated and philosophical grounds where it began. I think where a lot of us were kind of looking for the show to go. So I found that very exciting. And of course, and it's just, we'll talk about this more. It was very interesting to hear Carl Sagan's voice and Carl Sagan's phrasing juxtaposed with Neil Tyson's voice. And of course, that's in the new show, Neil Tyson is speaking really through he's speaking the words of Andruyan, Carl Sagan's widow. So I thought it was interesting juxtaposition. I'd like to hear some other people's thoughts about that as we go on.
Yeah, I mean, I will agree with Corey. I think it was really appropriate to sort of have the things that we don't totally understand take the focus for the last episode in the series. And I agree. I think it was really interesting to sort of hear the words of Carl Sagan that are so kind of, I guess, famous, really, and then to hear Neil deGrasse Tyson talk about sort of the similar themes, at least. So yeah, I mean, I agree. Like, ending it with Voyager, it's like kind of great and poetic in a lot of ways.
Yeah, I of course I liked this episode because it was heavy on astronomy, which is obviously a topic I like. Same with cosmology and dark matter and dark energy and kind of the crazy mysteries that we know a lot more about now than perhaps we did 34 years ago, especially dark energy, which didn't even know it existed then. And of course, as I mentioned in the summary, I really enjoyed hearing Sagan's words and the whole idea of Voyager going out into new space and what, not new space, but newly explored space, and what scientific endeavors can do. I just thought it was, I really liked it. It was a very fitting ending, I think, for the series.
Yeah, I thought it wrapped it up very nicely, and I like the fact that dark matter and dark energy, which are arguably two of the most important, if not the most important things astronomers are looking at right now, played such a big role in the final episode. So it kind of nicely summarized where astronomers stand right now in our knowledge of the big things in the universe, and then wrapped up with Carl speaking, and as always, Carl speaks very well, and it was nice to hear his voice again to wrap up the series.
Yeah. Sorry.
Just really quick, one thing that I think is really interesting is, you're reminded that normal matter, all this stuff you can see, everything that the last 13 episodes have talked about amounts to just less than 5% of our universe. And so if that's all these complex things amount to such a small fraction, imagine what scientists have left to discover about our universe and how exciting science will continue to be and discovery will continue to be in the generations later.
Yeah, and that's a great point. I was thinking some years ago, I was an editor at Scientific American. I worked there with John Horgan, who some of you may have heard of. He's a science writer and a science journalism professor at Stevens Institute of Technology. And one of his big arguments is that he really felt like that science was running out of steam. That once we got to string theory and these very elaborate, kind of sort of untestable theories of physics, that really, the process of discovering these big questions was kind of grinding to a halt. And he wrote a book about this, and the book that he wrote came out actually right before the discovery of dark energy. And I think I agree. Part of what was so beautiful about this closing episode is, one of the themes Cosmos has been hitting is the importance of asking questions and moving on. That every discovery leads to more questions, leads to more discoveries, and that's the real beauty of the scientific process. And so I thought it was wonderful to close an episode, after we've been hearing so many things that science has learned over the years, to close with an episode that's really about just how profoundly little we know when you pull all the way back. That there's still so much as was said beautifully, all of these things that we've learned about, all the things we've ever studied, if you want to take the pale blue dot analogy, every king and every commoner, every person who you've ever heard of, everything that we've ever studied is a part of that little 5% of the universe that we can see, and there's a whole other 95% that we don't even know what it is. I think it's a really exciting place to end, and a really exciting place to think about what comes next.
About 25 years ago, there was a book written by the astronomer Martin Harwitt, who some of you might remember. It was called Cosmic Discovery, and at the time, if I'm remembering correctly, Rich, you may remember as well, I think he estimated that about 23% of the kinds of phenomena in the universe were probably known about. And this is not to say that lots of things that we're going to discover are going to counteract what we know, or the laws of physics, or Newtonian physics, or Einsteinian relativity. But think of the incredible array of astrophysical phenomena that are yet to be discovered. Just to back up, Corey, what you said, that was Martin Harwitt making that statistical argument, writing about all sorts of facets of astronomy and astrophysics, and that was a quarter of a century ago. But still, we're in absolute infancy, arguably, about knowing about the kinds of things that are out in the universe. So that's absolutely right.
Yeah, you're right about Martin Harwood and his discoveries looking toward the future. And with this discovery of dark energy, we're probably up to about 23.5% now. But we still have a long ways to go before we realize everything that the universe has to tell us. And as someone much smarter than I once said, the greater the sphere of our knowledge, the greater its contact with the infinity of the unknown. So I think we're finding out how much we don't know as much as we are finding out what we do know.
Yes, and I think even the areas where we do understand the principles very well, the ways that those principles actually play out are often mysterious and baffling. I mean, and to me, the discovery of planets around other stars is a great example. Well, we understand perfectly well how chemistry works, how gravity works. You take a cloud full of gas and dust and you swirl it around a star. It's not a very mysterious process. You know exactly what happens. And yet, every kind of planet that we're finding pretty much has been a surprise. It turns out that when you just put a clump of gas and dust and you let gravity do its work, you get planets that don't look like anything in our solar system. You get planets that hug right against the edge of the sun. You get planets in wild, crazy orbits or backward orbits. You get things that are nothing like, not only nothing like anything in our solar system, but nothing like anything that anybody had ever predicted. So, and this is just starting from, from really a very familiar end of physics. Then, you get into dark matter and dark energy where we don't even understand the basics. Who knows what's out there?
Absolutely right. And time again through the history of science, things that you discover, phenomena in the universe, tend to turn out to be more complex than that which you anticipated over and over and over again. So there always is more that you're learning about the complexity of nature and of science than what you could anticipate from an earlier time. And that, quite frankly, makes it really exciting and really fun, doesn't it?
Well, I think we all think so, or we wouldn't be here.
Yeah. I actually think that it's something that Cosmos captured really well, too, is this sort of incremental idea of science, that there's always something more to learn and always something more to do. I mean, even just starting off with, Bruno at the very beginning and then sort of working our way up to Voyager and moving out into interstellar space. I mean, even that chronology, it shows how, long and hard the process of science can be, too. And also wonderful, obviously. So.
Yeah, actually, I keep stepping on your line. Liz, take it away.
No, you go ahead. It was just going to be something small.
Oh, I'm about to change the topic, so please, I defer to you.
I was just going to say that Neil also has mentioned numerous times about the fact that scientists know that they aren't always right. They have to question themselves. And I think that's also a big part of it, which he stressed and which we see numerous times throughout these episodes, is that scientists think you may have a theory one way, and then you do a little bit more observations, and it turns out that everything you thought you knew is not right, and it's actually this. And then you...
You're not referring to the BICEP 2 results, are you?
No, we don't want to talk about that. So much drama in that. I think we should, let's just wait until Planck releases its next set of data later this year, and then we can get back to that topic.
Okay, but he's just trying to tell us time and time again, scientists are people too, is the message there.
Exactly,
right?
yeah.
So actually, just picking up that thread, I think in many cases we talk about, how we've talked a bit about how Cosmos told a lot of the scientific stories as biographical stories about stories about individual people. There's actually a lot of interesting biographical material that did not make it into this episode, but this was more of a big theme episode. And I thought one of the stories, Victor Hesse, who discovered cosmic rays, there are many interesting aspects to his story, which obviously the episode didn't have time to talk about. First he noticed that there's this ubiquitous radiation that he picks up from the ground. Then he sent an instrument to the top of the Eiffel Tower, and the radiation seemed to be stronger at the top of the Eiffel Tower than the bottom. Then he did a series of balloon experiments. Then he did a balloon experiment during a solar eclipse and concluded that this had to be radiation coming from space and not coming from the sun. But actually, then there's a whole lot more story that goes on after that. Victor Hesse was working in Germany. He had a Jewish wife. He was threatened by the Gestapo and basically told that that if he stayed, he was probably going to be arrested. He fled to the United States, where he became part of the faculty of Fordham University, and then became an expert in nuclear fallout. Again, thinking about how radiation moves through the environment. After World War II and the atomic bomb, he became an expert in nuclear fallout. He studied environmental radiation. He was one of the early people studying radon exposure and how natural radioactivity from the Earth affects us. He put all these different threads together, and this seemingly very esoteric piece of research about radiation coming from space actually turned out also to connect to the environmental radiation that has human health effects, to nuclear fallout, which helps turn the tide against nuclear testing. All of these things are connected, and it's really to me it's that kind of story that I think Cosmos has been very, very powerful in helping people understand, which is that no discovery is made in isolation, and the quest of knowledge is not this little compartmentalized thing that's walled off from our lives. All these things connect, And so I think we're going to be talking today a lot about dark energy and dark matter, which seem very, very remote from people's lives, but the process of discovery that leads to those things and the kinds of insights that spring from them, it's all connected. There's no way to lead a life in which you benefit from science and technology and not have that benefit come from every single direction.
And then, of course, Fritz Zwicky.
I dare anybody disagree with that.
Which is why we're quiet.
I think we're in total agreement, Corey. And yeah, let's talk a little bit more about Victor Hesse, a very interesting guy, and then it's hard to draw up a guy who was more interesting with the eccentricity of his ideas, many of which were spectacular and correct, and others of which were sometimes peculiar in Fritz Zwicky.
Yeah, Fritz was certainly one of the more interesting characters in 20th century physics. As we talked a little bit before, he was the person that coined the term supernova for these objects that occurred in other galaxies that seemed to be much brighter than similar kinds of explosions seen in our own galaxy, which were called nova. So he coined the term supernova and then made the startling prediction that turned out to be right in the late 1960s, that these massive stars that explode give birth to neutron stars, which are incredibly bizarre objects that basically consist of nothing of neutrons, because the electrons and protons have been all squeezed into a ball so tightly that they became neutral particles called neutrons. He also did many other interesting things. As Neil mentioned, he was the first one to observe gravitational lensing in galaxy clusters, and this was something that Einstein's general theory of relativity predicted, but no one had seen it before looking at the galaxy clusters. And most importantly, in looking at these galaxy clusters, he realized that the galaxies are flying around much too fast for them to hold together over the age of the universe, and therefore there must have been some dark matter in there. At the time, he thought probably somewhere between 10 and 20 times as much dark matter as matter, but it turns out now there's probably closer to about 6 times, but still he had the right idea for how much was out there. But he was a very interesting person as well, and Neil kind of told a little bit about that, but he was very cantankerous, had run-ins with most everyone that he ran into when he was working at Caltech later in his career. A lot of people didn't believe lots of the things he said, including about dark matter and about neutron stars, because there wasn't really good evidence beyond what he had come up with, and people tended to ignore what he said. So he, perhaps rightly, viewed many of his colleagues as working beneath where he was and wasn't afraid to tell them what he thought of them, which is kind of interesting and not necessarily in keeping with what people tend to think of scientists as, but as Neil also mentioned, scientists are people too, and they can have opinions that are not necessarily what we think they might be.
Yeah, there's so in the science journalism world, or in the history of science world, there's a whole set of lore about Fritz Zwicky, and sometimes hard to separate the stories that are true from the stories that are apocryphal. One of the most famous stories is that he would call his enemies spherical bastards, because no matter which way you look at them, they're still bastards. And whether or not that's true, a little hard to say, because what happened over the years. As Rich was saying, Zwicky was a very intense and cantankerous personality. His ideas were in many cases well ahead of where observation was. So he had ideas that seemed untestable, or at least they were sort of hard to really prove. And so he ended up in this unfortunate position. He had these very prescient ideas. He got very frustrated that he couldn't convince everybody that they were right. And the way he approached that was, rather than trying to bring everybody else along with him, he basically railed against the stupidity of the world. And it turns out that's not a great way to convince everybody else that you're right. So he had in some ways a rather lonely scientific career, and his name obviously is not that well known outside of people who really know the history of 20th century astronomy and cosmology. I feel like I have a little bit of a personal relationship with him. I used to get letters all the time from his daughter, Barbarina, I suspect that people at Astronomy Magazine have received letters from Barbarina as well.
Yeah.
Barbarina was and is a very, very active defender of her father's legacy, and I would say, often in the same way, in a very aggressive way. And I feel a little bit bad for her, much the same way I feel bad for her father, which is that she has the unfortunate combination of being right and going about being right in exactly the wrong way. So back to that point of scientific personalities and how scientific ideas are established. Science is a human process, and persuading people of your point of view is itself a human process. Collecting data is important, but also doing it in a way that encourages people to actually look at your data, that turns out to be important too.
All right, well, let's take a Twitter question that rolled in, and we have a lot to talk about here yet, but we'll go to a question because it rolled in so quickly. How can we be sure of the accuracy of our estimate of how much regular matter is in the universe, creating the need for dark matter? Let's talk about Planck and its estimates of the composition of matter energy for a moment, if we can. Liz, that's in your wheelhouse, isn't it?
Yeah. I'm trying to think of a way that's not going to take up the next 30 minutes. So one way, Dave mentioned Planck, which was a radio microwave satellite. It ended a couple months ago, but it was basically mapping the microwave radiation across the sky that is remnant radiation left over from a time just a few 100,000 years after the Big Bang. At that time after the Big Bang, it was infrared radiation, but the universe is expanding, and that expansion has stretched those wavelengths to radio wavelengths, radio microwave. So by studying that light, scientists can kind of figure out the initial composition of the universe and what it was like at those few 100,000 years after the Big Bang, plus sort of what that light has traveled near, around, through in the time since. So galaxy clusters tend to be filled with a heck of a lot of hot gas in addition to the galaxies. And so when those microwave photons, particles of light, happen to travel through that hot gas, they get affected in certain ways that scientists can sort of analyze, and they analyze a whole bunch of them statistically and can figure out kind of a map of the universe and how mass is distributed and how much dark energy existed, or this mysterious force that's accelerating the universe's expansion. They can figure out roughly the percentage of the total energy in the universe that is regular matter, like atoms and electrons, that is this dark matter stuff that is dark energy. So they can tease it all out of the CMB, which is a pretty awesome thing. So that's one of the most amazing images, I guess you could say, in astronomy, even though it may not be the most gorgeous one, although I guess depends who you talk to. I think it's a pretty awesome and very pretty picture. But
so if I can just pick up that thread, I think so. To me, what's really remarkable with the dark matter story is, this is a true classic science detective story. You had Fritz Zwicky finding one line of evidence, which is that there seemed to be more gravity holding galaxies together than he could account for from the stars and gas that he could see in his telescope. And part of the reason nobody believed him is that didn't seem like enough evidence. So then in the 1970s, you had Vera Rubin looking at how galaxies rotate. And again, there seemed to be a lot more matter holding the galaxies together than you could account for from the light you can see. So there's another line of evidence. Then you look at the theoretical models of how the universe formed and the kinds of nuclear reactions that happened right after the Big Bang. That tells you how much ordinary matter there should be versus the total amount of mass that you seem to see in these galaxies. And that's another thing that tells you that the amount of ordinary matter is not nearly as high as the amount of total matter that you see out there. Then you have these measurements of the microwave background Liz was describing, where you can actually see basically how the early universe was reverberating and echoing, and that also tells you what it was, the composition, and you get another number from there. And then you look at how matter is bending light from distant galaxies and how much you weigh the universe that way. So at this point, there are maybe 7 or 8 different ways that you can put the universe on a scale and figure out how much is out there that you can see versus how much is out there that you can't see. And the amazing thing is, they all give you the same answer. These are different techniques coming from different approaches, and they all give you the same answer. And when that happens, each one of them individually is circumstantial, but when you put them all together, I would say the evidence is overwhelming that dark matter is real. Now, the problem is, we still don't know what it is. Nobody has been able to find a particle of dark matter, and that's one of the great next steps in science, is trying to figure out what that stuff is. But the step-by-step investigation that takes you from something that seems, frankly, just too weird to believe to something that now everybody believes, I think that really is one of the most remarkable detective stories in modern science.
Yeah, definitely. I'll throw in one little word of caution. Isn't probably the right word, but there are a few scientists out there that probably are about on the same level as climate deniers that don't think the climate is changing. But there are probably 5 to 10% of astronomers that think that they may just not understand gravity 100%, and that perhaps gravity on the weakest scales is a little bit stronger than Newton initially thought way back in the 17th century when he came up with his ideas. They have a word for their theory which is called modified Newtonian dynamics, and there are some successes in its explanations of what we see in the universe and some notable failures as well. So there are some people out there that are looking into this theoretical aspect of it that could possibly play a role, at least, in the dark matter debate. But I would agree with everyone else that probably at least 95% of the scientists out there think dark matter is real, and we just haven't found out what it is yet.
Yeah, no, I think you're right. That's an important note of caution, that we should never get too smug when we say, oh, we know everything, because history says that every time you get a little too smug, nature slaps you down. But I was talking recently with George Astasio. I may have mangled his last name. He's the primary scientist who works on the Planck mission, and I asked him what he thought about these other ideas about dark matter. And although he said it in more polite terms, he basically said, "Cuckoo."
Well, let's talk a little bit more about dark matter. Have we not? If dark matter, here's another question that we have. If dark matter exists in all gravities, shouldn't it have an effect on our solar system? Why can't we detect it close by to us? Why is it that the Milky Way, if it has lots of dark matter, which we believe it does, why is all that out in the halo?
It's very diffuse. Just the way that normal matter sort of, when galaxies started forming, normal matter settled because it interacts via electromagnetic forces. So that means if it rams into each other, it can change it basically lets out some heat. And so by doing that, it ends up losing some energy and kind of settles toward the center. So in our Milky Way, we have all the luminous matter sort of sitting in this bulge in the center, surrounded by a disk. And the dark matter stays diffuse, and it stays roughly the same density everywhere. So it extends way farther out than our luminous disk, whereas the luminous disk is maybe 120,000 light years across. This dark matter bubble, halo, whatever, cloud, extends, I think it's almost like 10 times as far out, if I'm remembering the numbers. And because of how diffuse it is and how big it is, it does actually end up weighing a lot more, I guess. The bulk of that weighs a lot more than the luminous gas and stars.
Yeah, and one point to follow up on what you just said is that that means there is dark matter in our solar system, but it's just so diffuse that we don't see it at all. But it does give us the opportunity that if it is out there and the experiments exist, we can find it. We don't have to go out into the halo to find what these dark matter particles might be.
And scientists are looking for it in experiments that Corey's about to describe.
Wow, I didn't even expect an intro like that. I was actually going to let me start by following up. So this idea of if dark matter is all around us, why don't we see it right nearby? Why don't you see it in the solar system? In fact, it's a question we've been asked before, and I posted an answer about that on my blog, and I think it ran in Discover magazine as well. The answer is you can look at how even nearby stars move and estimate how much dark matter there is right in our neighborhood, in our part of the galaxy. And it can be there. It can be there even in fairly significant amounts, but on the very local scale, it's hard to detect. And if you then just extrapolate how much is within our solar system, it turns out the amount is so small, it's completely unmeasurable. And the reason for that is, just as Liz was saying, dark matter is spread out over very, very large scales. And that's entirely, the two ideas are completely consistent, that it would accumulate to have a very big effect over very large scales. But it's basically, if you're surrounded by it on all sides, locally it's actually very hard to detect. There is a new satellite called Gaia, which is measuring the movements of about 1 billion stars in our galaxy with extreme precision. And Gaia is going to make a much, much better estimate of how much dark matter is within our galaxy and even within our neighborhood of the galaxy. But yeah, it's a good question. Dark matter is out there, we're pretty sure. But again, nobody's been able to find this stuff. And so what you really want to do is find a dark matter particle, find a little piece of the stuff. And so there are a number of different experiments that people are doing. People at the Large Hadron Collider are trying to basically create dark matter directly, where you wouldn't see it, but what you would see is you run a particle interaction and it looks like something is missing. It would tell you that essentially, a dark matter particle escaped from your detector. There are people who are looking for reactions that happen when a dark matter particle happens to collide directly with a particle of ordinary matter and would leave it would deposit a little bit of energy as heat. And people are looking for that, and there are a bunch of experiments like that running around the world. And then one of the theories is that dark matter particles, if they bang into each other, would become visible. That the two dark matter particles smashing into each other would destroy each other and create visible radiation. And there are people looking for that. And if you really pay attention to the scientific literature, there are people all the time saying, "Hey, I think I saw dark matter." And pretty much every time they've said that, the reaction to almost everybody else has been, "Hey, yeah, we don't think you did." But there are some very interesting results that people have not explained that might be dark matter. And it's possible that we already have picked it up, and we just haven't quite been able to prove it yet. But I think the people who study it are very optimistic that in the next maybe 5 or 10 years, possibly even sooner, we're going to get a detection that really stands up. Where we really start to say, okay, now I get it. Now I know what this thing is.
Physicists also at the Large Hadron Collider in Europe, when they're upgrading stuff right now, and it should be upgraded in, I think, late 2015. And some physicists say that if once that's upgraded and in the full energy, the full power mode of what it will reach, if it doesn't generate these dark matter particles, then we need a new theory, because the energy levels it will reach should be making these dark matter particles called neutralinos. So we'll see what happens when the LHC is back up and running at full power.
There's also the alpha magnetic spectrometer, I think, on the space station. So there's a tool on the station that's actually looking for these interactions and searching cosmic rays and trying to figure out if there is dark matter. And they made some kind of announcement maybe a year ago, something like that. I can't for the life of me remember what it is right now, but I think it was some upper limit was set, something like that.
Yeah, a lot of experiments have done upper limits and been able to or lower limit, one of the two. They've been able to sort of constrain where other experiments will hopefully find it. But and that is an increase, and that's a better thing for finding it. But they haven't found it yet, so.
Right. Again, right. So Miriam, the experiment you were referring to, the alpha magnetic spectrometer. So again, what it directly looks for is antimatter. But antimatter, again, if these dark matter particles either decay or they crash into each other in a way that produces a visible effect, one possibility would be that you would see gamma rays. One possibility is that you would see particles of antimatter, either one of which is in principle detectable. So the spectrometer on the space station is looking at antimatter particles and sees an excess which might be, which sort of fits in with the theory of dark matter. But it's one of those things where you're so many rungs up the ladder of speculation that if your theory of dark matter is right, and if your theory of how it decays is right, and if your theory of what you're seeing in your detector is right, and if you work your way through all these ifs, you might have found something. So I think Sam Ting, who runs the experiment, was very excited about the result, and certainly the kinds of measurements he's making are phenomenal. But whether or not that's dark matter, there's still a lot of skepticism.
Okay, here we have another question. Comment from Jim Nelson that might lead to a discussion. Considering how much Cosmos left out about the cosmos, when does Season 2 begin?
So my DVR totally said this was Season 1 finale when it recorded it. So I don't know if that showed up to anyone else, but I was pretty excited that might mean there may be a Season 2.
Also, it ended on a cliffhanger. If you can't end a show on a cliffhanger, they love like, oh, and by the way, there's a dark universe. We need Season 2.
Surprise.
There's actually, it's kind of funny because they have not said whether or not they're going to do a Season 2. I think it's probably unlikely since the first season took something like some ridiculous number, like 7 years to actually make it. So it was, I'm sure it was in some way, a moderate success, at least according to like Fox numbers and everything like that, but I actually think there's so much energy and time put into making one season. It might be another 7 years before they're able to do another season. But I haven't heard one way or another if there will be a Season 2 or not.
Yeah, certainly the original plan was for it to be a reboot of the original Cosmos, and as such it was going to be a single run of the 13 episodes. If enough people are interested and there's an audience out there for it, I could certainly see that they might be interested in going back and doing perhaps single episodes about certain topics. But I have a feeling we've probably seen the last of a full season worth of Cosmos.
Yeah. Maybe we can create our own. It'll be a much lower budget, but there's still some science topics we didn't touch on that we could definitely do.
Yeah,
a weekly Google Hangout.
Yeah,
I'll have to work on my billions and billions.
Look, they did 13 one-hour episodes. We did 13 one-hour episodes. I mean, we could do this again. I think their audience was a little bit larger than ours, but I think ours is small but very, very dedicated.
Well, they did touch on, but they didn't talk thoroughly about a lot of science that has happened since 1980, since the first Cosmos aired. What do you think in terms of comparing and contrasting Carl Sagan and Neil Tyson? How did the new series do stylistically, with Carl not there writing, with Annie and Steve Soder doing the writing, with Neil presenting? Is there an interesting compare and contrast between Neil's Cosmos and Carl's Cosmos?
So,
no, Aaron, it's all you.
Okay. So I was just going to say, we were all kind of discussing this a little bit earlier, but I think that it was pretty telling that maybe for me at least, the pinnacle of the entire 13-episode run was actually hearing Carl give the pale blue dot speech. And at the very end of this, for me, I thought it it was the most powerful moment of the entire show. So actually, just sort of having that in mind, I mean, comparing Neil and Carl, I actually in some ways think it may not even be a fair comparison, just because, you know, Neil is following in Carl Sagan's footsteps. So to actually pave his own way is really difficult. I mean, I thought he was a great presenter and did some really interesting things, and I loved the writing, of course, but I also think that it was truly a reboot and in many ways an homage to Carl's original series. So looking at it on its own merit sometimes I think is hard.
Yeah, I agree. I mean, it's a tough act to follow, and especially, you know, I mean, Carl Sagan was speaking from the heart. I mean, it was his show, it was his writing, it was his passion, and I think, you know, that pale blue dot speech, you know, I don't know how many times I've heard it, but when it unspooled again at the end of this last episode, I got chills listening to it. It is, you know, it is something, you know, it is such a profoundly beautiful way of looking at the world. And, you know, and that was really, I mean, that was Carl Sagan's poetry. And there's something very different. You know, Neil Tyson is an incredible science communicator, and I think he was a powerful presence on this show, but there's no getting around the fact that he's fundamentally reading off a teleprompter. You know, he's reading Andrian's words, and he's giving them his own inflection and his own passion, but, you know, this is not his personal project the way it was Sagan's. And I think that's, you know, that's a big difference. And I think obviously, you know, it creates a different kind of show. I think it gave the new show a lot more leeway to go places where Carl Sagan, you know, didn't or couldn't go. But I did really miss that sense of you know, personal voyage that the original was, because it's so rare that you get to hear a scientist speak so unabashedly from the heart. I mean, I think, you know, Sagan was never afraid of being corny or being too popular or wearing his heart on his sleeve. You know, he just put himself all out there. I think that's what made him such a revered figure. Is that he was doing great science, but he was also just, you know, he was absolutely, in the very best sense of the word, he was shameless. You know, he did not feel the inhibitions that so many of us feel about speaking from the heart. And, you know, you don't see that on TV very often. And as much as I enjoyed a lot of the current Cosmos, it doesn't have that same feeling. You never felt that Neil Tyson was putting himself in a dangerous place by what he was saying, the way that Carl Sagan was.
I would agree 100%, and just to be fair, I think Neil Tyson would probably agree as well. Knowing his relationship with Carl, I have a feeling he would say the exact same thing as well.
Well, you know, Neil's going on a speaking tour. Actually, he's going on a stadium tour. The news release just went around today that starting the end of this year and into 2015, I think, he's going to be playing basically concert houses around the country, doing presumably riffing on some of the themes from Cosmos. And I'll be very curious to see what happens there, because I think that's where we'll really hear Neil being Neil, and hearing, you know, when he gets to have just full throttle his own voice, how does he want to express these themes?
Okay. Go ahead.
Go ahead.
Are we done with? Have we concluded that thought?
Yes.
Okay. Before, and then we'll move on. We have another question. This is from Brian Stevenson. I love Cosmos, but have a problem with a certain concept presented by the show. If the Big Bang created space and time, doesn't the phrase "before the Big Bang" have no meaning at all? This is someone after my heart. How can something precede something in time if time is not created yet? But Tyson used this phrase at least 3 times throughout the Cosmos episodes.
That's a very good question.
There's a way to answer it.
Yeah, people don't know. There are different theories about maybe our universe is one of these cyclical universes. So maybe this is a start of time, but there was a universe before that condensed and then bounced back out to restart time. I don't see how there's any way that scientists could ever know what happened before the Big Bang. I don't understand how any evidence could ever tell them this, because we can only see as far as light can travel in the amount of time, 13.82 billion years. And even if they observe any sort of signals directly from inflation, which was a fraction of a second, I mean, at 1.43 zeros, 1 of a second after the Big Bang, that's as far back as they could ever see would be the signals from that, if they can detect them. So, yeah, that whole thing weirds me out. I don't know. It's a part of cosmology that is pretty wacky, and I have a hard time wrapping my brain around it because it just doesn't work in the sense of time and how time flows, at least in the way that our universe exists. Okay, does someone else have a better insight on this?
Oh, I'm sure it's not a better insight, but you're right that the theories are out there for things that may have given birth to our universe, and so we may not be able to go back and see something that happened before our universe, but there are what most people would consider pretty wacky ideas out there of things that we could possibly see that would imply that ours is not the only universe. If you buy into the fact that there's a multiverse with many different universes in it, it's quite possible that at some point in the distant future, our universe may run into another one of these universes, and for a split second anyway, we might have a revelation that, oh, there are other universes out there before it totally destroyed us. So there are ideas out there that our universe may not be the only one, and therefore, if we can determine the underlying structure of this multiverse, we might have a way of learning more about what gives rise to these things. But I would say, as Liz did, that the odds of us finding that out in any of our lifetimes is pretty slim.
Well, here I'm going to step forward and be the wacky guy then. So earlier Liz was describing the Planck mission and the relic radiation left over from the Big Bang. Well, when you make a map of this radiation in the sky, there's some weird things. Basically, one half of the sky looks a little bit hotter than the other half of the sky, and there are a number of weird features about the structure of how the radiation is distributed that don't quite match what people expect from the models. Basically, the whole universe looks to be a little bit lopsided. Well, you know, that might be just random statistical noise, or that might be an indication of something bigger. One of the theories, a number of researchers, a cosmologist named Laura Mersini has been one of the big people pushing this idea, is that the reason that the universe looks lopsided is that our universe may have actually been entangled with another universe when it was born. That this is quantum entanglement on the very, very large scale. Well, it's a pretty weird idea, but if she's right, this is not observational evidence that you have to wait, decades or centuries to see. We actually have evidence of it right now, and I think the difficult problem with this theory is not that it's impossible, but that right now it's not clear how you prove it or how you distinguish it from other explanations. But it's certainly it's an interesting interpretation. It's an interpretation that actually does exactly fit what we see, and that accounts for something that really cannot be explained in any other way. And so again, when I was talking to the lead researcher on Planck, usually when you talk to the observational people and you talk to them about some weird theoretical interpretation, observers tend to be pretty conservative, and they usually say, they usually tell you something sort of dismissive about, well, yes, the theorists always have their ideas. And when I asked him about this particular idea, about the Laura Mersini idea that our universe is sort of tangled up with another universe, he said, oh yeah, that's actually a really interesting idea. And he started trying to figure out, how you would test it. So, as mind-boggling as it may sound, people are thinking right now about how to do this seemingly impossible task of, finding other universes and maybe even figuring out what those other universes are like. Now that still wouldn't tell you, is time infinite? What was happening before the Big Bang? Was there a before the Big Bang? But if you could really come up with a convincing observational and theoretical case that there are other universes, basically, if there are other universes, then the beginning of time here was not the beginning of time. It makes at least a strong circumstantial argument that our universe might be finite, but the universe of universes, the multiverse, is infinite, and then all of a sudden the idea of before the Big Bang makes sense, and the idea of a beginning doesn't make sense. Who knows if we're really on the right track, but there's at least a track, which I find exciting.
We may be back to the steady state theory all over again.
Well, yeah.
Well, and just to be fair, we held the climate deniers to this standard when, telling them that if you believe in scientific principles, you have to believe in them all the time, not part of the time. These are multiverses, and something prior to the Big Bang are possibilities or plausibilities, hypothetically, mathematically, but there is no evidence. Untested hypotheses opens up a big range of all kinds of fun things. Right now, as of this moment, these are not within the realm of science. And the theory, quote unquote, still has to be observationally tested and verified, as in Einstein's theories. And then they go from hypotheses to theories. So we really don't know. It's tempting to talk about multiverses and something before the Big Bang, but there's no evidence as yet, which is not to say that we shouldn't continue to investigate, of course. But they're not on par with other things that are observationally verified pieces of science at this point in time. Just to play the role of curmudgeon for one moment. Okay, here's another question for us. If we wanted to do another big science mission, imagine that Congress, or certainly other countries more likely, are interested in funding big science missions, like Voyager, like the Voyager craft. What should that be now? Where would we turn if we had a Carl Sagan Voyager-like grand exploration of the solar system, of astronomy, of other star systems? What would appeal to you in terms of a grand exploration at this point in time?
Gravitational waves. With everything that scientists have learned by studying the electromagnetic spectrum, it's one type of message carrier. Gravitational waves gravitational radiation exists, and the thought is that they move as waves and sort of wave-like oscillations. Imagine what scientists will learn about the universe when you have a whole nother messenger, a whole nother window to look through. And gravitational waves can vary from really high frequencies, which is similar in the way that gamma rays have really high frequencies in electromagnetic radiation, and gravitational waves go all the way to the really long wavelengths. So it would be I'm glad that there's a mission on the books, per se, for 2034 from European Space Agency, but I hope that it is something that NASA can seriously also get involved with, because a full-scale mission like that has some really amazing prospects for the future.
As Kip Thorne says, colliding black holes, the brightest objects in the universe, but no light.
Yeah, they would generate some pretty intense gravitational waves.
Other ideas for the ultimate dream next generation mission?
Well, if we're talking about exploring the solar system, here I would say three things that I would really like to do. I would like to put a rover on Venus, and then I would like to do a flyby mission. You could double them up. You could have two spacecraft of the exact same design. One that would fly, that would do very close passes over the surface of Europa and sample water plumes coming from Europa, and another one that would fly very close past Enceladus and sample the water plumes coming out of Enceladus. A Venus rover mission would tell you a lot about how planetary geology works, and probably tell you a lot about how the Earth formed. And flying through those icy plumes from Europa and Enceladus will tell you, or it would give you a very good clue of whether or not there is life in either of those places. Those are the two other places in the solar system where we know that there are large bodies of liquid water, which we think is one of the key things for supporting life. They actually would not be terribly difficult missions. They could even be sample return missions that would bring the stuff back to Earth. And you could do all three of those things for, I would estimate, about $5 billion, which is a little less than 1/3 of 1 year of the NASA budget. So it's not, it's not outside the realm of possibility. It's just outside the realm of political reality.
Yeah, and I'll just throw in my 2 cents worth is that I think Voyager was unique in the sense that it managed to visit 4 different planets and many, many, many moons of those planets, 2 of which had never been seen before and 2 of which had been seen only very crudely by previous spacecraft. And so I think the kind of level of observations that it was able to do over such a wide range of objects that people were familiar with and were interested in probably isn't something that is going to happen in the solar system, so we may have to go beyond the solar system for something like that. Although keep your eyes open next year for the mission to what Neil deGrasse Tyson would call the first of the non-planets beyond Neptune, when New Horizons arise at Pluto, and that should be exciting for everyone.
Yeah, I would be really interested in seeing another mission, to the kind of the edge of interstellar space, but actually that was made to go there and take measurements of it in a real way. I mean, I remember talking to someone about this one mission that was just sort of this kind of extreme idea that would be sending out kind of this mothership with a fleet of small CubeSat-sized satellites that it would get out to like the heliosheath or some very distant part of the solar system, and then unleash these satellites that would then model and take measurements of this part of the solar system to kind of see what is actually happening. To have more than just the Voyager data, I think would be really interesting.
Oh yeah, a dedicated interstellar mission, and actually, and one final thing. A mission to observe planets around other stars directly, which again, that technology is under development right now. $1 billion would give you a Pathfinder mission. $3 or $4 billion would give you the full-blown thing that would let you take direct images of Earth-like planets around other stars. I mean, they're not going to look like pretty pictures. They're going to look like just a few pixels, but that would give you enough information and enough light to start to say, are those Earth-like planets, do they actually have, do they have water? Do they have atmospheres with oxygen and possibly even evidence of biomolecules? That would also, I think that's probably one of the other big frontiers. Back to Rich's point, that looking beyond our solar system, being able to study and start to understand those planets around other stars, and really whether or not there's evidence of life on planets around other stars. That would be huge, and I think that is something that, even though visually it won't be very exciting, conceptually that seems like something that I think really could be electrifying to the public.
The key is to get $3 to $4 billion for a mission, which,
right,
as you've already mentioned, is political reality, not so much.
Start a Kickstarter.
Yes.
And remember that a ground-based telescope, even like the Colossus telescope project that some people have talked about, that would be maybe a paltry couple of billion, at 74 meters, aperture could potentially directly detect infrared from a civilization, and you could determine that it's from a civilization and not from rotating volcanoes on a planet and so on. So there's some exciting things that can be done from the ground as well. And as Rich says, we've got a pretty exciting year coming up next year, starting in July of next year. And actually the data from New Horizons will be sent down over a period of about 16 months. So that's going to be sort of a prolonged, drawn out, if you will, exploration, even though it's a flyby, of Pluto and Charon and friends next year. So that'll be pretty exciting and interesting. Well, I'm afraid that that's all the time that we have today. Thank you so much to our panelists again for an outstanding final chat. Corey, thanks again. you've been terrific all the way through here.
Well, it's been fun. It's been a lot of fun.
Liz, thank you once again for being here.
Yes, thank you.
Miriam, it has been a great pleasure, and we hope that you'll come back and join us for a hangout about something that's not Cosmos.
Yeah, absolutely. Thanks for having me.
Rich, great fun as always. Thank you so much.
I had a blast.
Excellent.
And Dave, thank you for your moderating throughout. And I'm really looking forward to our weekly hangouts about Big Bang Theory.
Yes. Yeah. Well, we start next month.
Yeah.
Sounds great. Thanks again to Celestron for sponsoring this series of Cosmos Rewind Google Hangouts. We're very appreciative of their support, of course, as always. With the series ending, Astronomy Magazine and Celestron are sponsoring a special contest for those who have enjoyed Cosmos through the end of June. Just share with us what the series has meant to you overall, and you'll be entered for a chance to win a Celestron Cosmos 90 GT Wi-Fi telescope. You can enter today at astronomy.com. Thanks again for joining us on this 13-episode journey. If you have any topics you'd like to see discussed in a future Google Hangout, Big Bang Theory or otherwise, please email us at letters@astronomy.com, and we'll be happy to hear your feedback. And thanks again personally from me to all of you, and for all of the folks here, Kevin Keefe, our publisher, and Carrie Stock, and Lisa Raffensperger, and everyone else who has made this a real pleasure to do these Hangouts. We look forward to being back with you soon on slightly different topics. Thanks very much for joining us, and have a great week.